All right, let's talk about something that seems, well, completely impossible. We're going to challenge a rule of logic so basic you've known it your whole life: how to count. So what if I told you that in the quantum world, you can put 3 pigeons into 2 holes and somehow find that no 2 of them are ever sharing? Yeah, let's dive into how that could possibly be true. So here's our game plan. First, we'll lock down the classical counting rule that seems unbreakable. Then we'll see how quantum physics just shatters it. We'll look at the very specific recipe you need to make this paradox happen, check out the real-world experiments that prove it, and finally, try to wrap our heads around what this all reveals about reality itself.
Okay, first things first. Before we can break a rule, we have to understand just how solid it's supposed to be. And this is a real cornerstone of how we think the world works.
It's a pretty simple question, right? You've got 3 pigeons and only 2 boxes to put them in. The answer is just obvious. At least 2 of them have to end up in the same box. There's just nowhere else for them to go. And this gut feeling, it's actually a formal, powerful rule in math and logic. It's called the Pigeonhole Principle. And it feels less like a theorem and more like a simple statement of fact. If you have more things than you have places to put them, something has to double up. It's a guarantee. It feels like logic at its absolute most certain. And this isn't just some abstract idea. You use it all the time. It's why if you pull 3 socks from a drawer that only has 2 colors, you're guaranteed to get a matching pair. It can prove that in any group of people, at least 2 of them must have shaken the same number of hands. It even proves, and this is wild, that there have to be at least 2 people in a city like London with the exact same number of hairs on their head. Why? Because there are just way more people than there are possible hair counts.
Okay, now that we've established our unbreakable rule, let's head into the quantum world, where things get turned completely upside down.
So, we start with our 3 quantum pigeons. In a real lab, these would be tiny particles, like photons. And we're going to guide them toward 2 pigeonholes. These aren't physical boxes, of course. They're distinct quantum states. For a photon, you can think of these as its polarization, say horizontal or vertical. And here is where our brains start to melt. When scientists perform a very specific kind of check on this system, they find that no 2 particles are in the same state. I'll say that again. 3 pigeons, 2 holes, and nobody is sharing. How is that possible? This really gets to the heart of the quantum weirdness. See, classically, a pigeon is just in a hole. Its location is a pre-existing fact. We just look to see where it is. But a quantum particle can exist in a superposition. It can kind of be in both holes at the same time. And when you measure it, you're not just passively looking, you're actively forcing it to choose. So the properties of these quantum pigeons aren't fixed. They literally depend on how you look at them. So how on earth do physicists actually set this up? What's the secret sauce that makes this seemingly impossible thing happen? Well, it really comes down to a kind of 3-step quantum recipe. First, you have to carefully prepare each particle so it's in a superposition of being in both states at once. Then, and this is clever, you perform what's called a weak measurement. You're peeking at the system so gently that you don't force it to collapse. And finally, and this is really the key, you post-select. You run the experiment a bunch of times, but you only look at the results from the runs that end in a very specific, strange final state. It's like you're filtering through all the data to find only the most miraculous-looking outcomes. And what's so strange here is that the particles start out completely independent of each other, and in that special final state that we filter for, they're also completely independent. So all this bizarre coordination, this weird effect where they seem to avoid each other, it all happens in that unobserved time between the beginning and the end. Now you might be thinking this all sounds like a neat trick on a blackboard, but this isn't just a thought experiment. Scientists have actually gone into the lab and made this happen. In a real experiment, physicists used 3 individual photons as their pigeons. The pigeonholes were their polarization states, horizontal or vertical. Their gentle peak was a really clever setup with a beam splitter that could tell them if any 2 photons had the same state, but crucially, without revealing which state that was. And the result? Exactly what the theory predicted. For that post-selected group of photons, they found 0 evidence of any 2 sharing the same polarization. Now here's the kicker. The gentleness of that measurement is absolutely crucial. The experiments confirm that if you measure too strongly, if you peek too hard at the system, all the quantum magic just vanishes. The system collapses, and boom, the classical pigeonhole rule comes roaring back. The paradox only exists in this really delicate, non-invasive limit.
Okay, so what does this all mean? This isn't just some quirky lab result. This paradox has really profound implications. It's forcing us to rethink what reality even is at the most fundamental level.
You've probably heard of other famous quantum puzzles like the EPR paradox, which challenges our ideas about space and distance. This is a different flavor of weird. The pigeonhole paradox doesn't need the particles to be entangled from the get-go. Instead, it makes a direct assault on the very logic of counting. And the contradiction it finds isn't just statistical. It's an absolute, all-or-nothing logical paradox within that specially selected group of results.
And this has sparked a massive debate. On one side, some physicists say these weak measurements are giving us a peek at a deeper, truly bizarre layer of reality. On the other side, critics argue that it's not really a paradox at all, but more of a cleverly designed interference effect, where the whole experiment is set up so that the outcomes where pigeons do share a hole just cancel each other out.
But no matter which side of the debate you're on, what this paradox demonstrates so powerfully is a core concept in quantum mechanics, contextuality. It means that a property of a particle, like where it is or what state it's in, isn't a fixed fact just waiting to be discovered. The answer you get depends entirely on the context of how you ask the question, on the specific measurement you choose to make.
And this really brings us to the big takeaway. Our everyday logic, the common sense we rely on, even something as basic as counting, it's not a fundamental law of the universe. It's an emergent property that works for our big classical world. But underneath it all, reality is a much more fluid, contextual, and interconnected tapestry than our intuition can even begin to handle.
Which leaves us with a final, pretty staggering thought. The pigeonhole paradox seems to take the most basic rule we have for organizing our world and just breaks it. So if the simple act of counting isn't a fundamental truth about reality, then what is?